the question we're going to look at today is there a way to go around the graph in such a way that I visit every vertex exactly once? So for this, I want to remember the definition of a cycle. So a cycle in a graph is a walk. Remember, a walk is something where you just start at a vertex, you take a step along an edge, and then you step along an edge, and so on and so forth. And we say that a walk is a cycle if it has at least 3 vertices and it doesn't repeat any vertices. Maybe I should... Okay, let's... Maybe I really mean 2 here, at least 2 vertices. In any case, I think... So I'm not... By the way, I'm not going to ever mark you down for not completely using... So there's different ways to define things like cycles or walks and stuff like that. As long as you have the right idea, you're always going to get full points. But basically, the idea of a cycle is like this, okay? You start somewhere, you go around, you never visit the same vertex twice, and then you end up like where you started. Or if you kind of use this, if you use the definition of walk that or the definition of cycle maybe that we defined earlier, you could think of it as you end like here at the neighbor of, so suppose you start here, you could think of it as you end here, or that you end where you started. I mean, it really, I'm not going to, yeah, so it's not, yeah, so maybe that's part of this confusion. Let's actually just change this definition, just make it clear. So let's say it's a walk with at least 3 vertices, which ends, well, not at a neighbor of where it started, but ends where it started. Okay, I think that's going to be clearer. It doesn't repeat any vertices. Then it becomes annoying because I say I didn't repeat any vertices, but in some sense, the starting vertex gets repeated. So let's say it doesn't repeat any vertices except for the starting one, right? Because it starts where it ends. But you can see there's like, it's a little bit annoying to define this. But like I said, as long as you demonstrate in your solution that you got the right idea, I'm not going to worry about like, did you end where you started or a neighbor of where you started or whatever. I mean, that's not going to be an issue. Okay. So just, yeah, as long as you demonstrate you understand the idea. So this thing is not a cycle because, so you could think of this as a walk. Let's say you start here, right? You can go along this thing and end where you start. But the problem is that this vertex is repeated, right? And similarly, this is not a cycle because this vertex is repeated, right? So a cycle basically looks like a kind of circle with vertices on it. Now, a Hamiltonian cycle, or sometimes, so the terminology, you might see different types of terminology like Hamiltonian cycle or a Hamilton cycle. Both of these words are these terminologies are equivalent. So a Hamiltonian cycle in a graph is a cycle that includes every single vertex of the graph. So if I've got this graph here, where think of the black lines and the red lines as being edges of the graph, then if you look at it, the red edges form a Hamiltonian cycle, okay? Because if you take a look, if you start somewhere and you kind of walk along, you can see that it's a cycle. So it's a walk that ends up where it started. And if you look at the vertices, you'll see that every vertex appears somewhere on that walk or on that cycle. Okay, so it's just like I said, so the things we were doing last time, Eulerian circuits, that was a way of going around a graph so that you visit every edge exactly once. A Hamiltonian cycle is a way of going around a graph so that you visit every vertex exactly once. Okay, and in both cases, you have to end up where you started. Okay. There was also this thing of Eulerian trails last time where you don't have to end where you started, but a circuit, you have to end where you started. Okay. And yeah, so this really does sound very similar. I mean, at least I hope it sounds very similar to Eulerian circuits, right? There you were trying to visit every edge once. Here you're trying to visit every vertex once. But weirdly enough, even though they sound very similar, these are very, very, very different concepts. And I'm going to try to kind of illustrate that to you in some sense. So here's one way that they're quite different. Suppose I give you a graph and I just ask you, yes or no, does it have an Eulerian circuit? And I don't, so remember there was this Fleury's algorithm which you could use to find an Eulerian circuit, right? I'm not asking you to use that algorithm. I just want you to say yes or no. does it have an Eulerian circuit? Or is it an Eulerian graph? So can anyone tell me an algorithm? So an algorithm is just like sort of method of answering a question in some sense. So can anyone tell me a simple way of determining if a graph has an Eulerian circuit or not? Yeah, exactly. So there's an answer in the chat, which is exactly the right thing. You know, first of all, we want to check if the graph is connected. Well, it doesn't matter which order we do these things. And if it's connected, then you just go through the vertices one by one and you say, okay, is the degree even or is it odd? If it's odd, then you just give up or you just say, no, it's not Eulerian. If it's even, if they're all even, then you just answer yes. So there's a very simple algorithm to check. And that, weirdly enough, that algorithm doesn't even require you to find the circuit, right? As long as you do this check, you can know that it exists without finding it, which is kind of a weird concept. But Euler's theorem proves that this is true, right? That just by checking this, you can know if it exists. Right, so there's an algorithm, yeah, for a kind of simple algorithm for checking if it's Eulerian, but this is kind of difficult to kind of explain to you without doing things rigorously. And this is kind of beyond the scope of the course a little bit. But what I want to say is that there's no simple way to check if a graph is Hamiltonian. Okay, there's a simple way to check if it's Eulerian, but in fact, we know for sure that checking if a graph is Hamiltonian is a hard problem. Okay, in some sense, we know it for sure. Okay, there's an issue about whether, so if anyone knows about P equals MP problem, so if P is not equal to MP, then we know this is a hard problem, but let's not get into those technical difficulties. The point is, there's no good way to check if something is Hamiltonian. And this is what I was kind of alluding to on the previous slide, that it's a so-called NP complete problem to decide whether or not a graph is Hamiltonian. Okay, so this is, you don't really need to know what this means, this NP complete thing, because I'm not defining it. It's not really part of this course. But the only reason that I kind of mention it is that, well, first of all, it's good to be exposed to these things just for your mathematical background, even if I don't really say what it means. But second of all, it's just to illustrate the fact that these two problems are very different. Okay, so it's hard to check if a graph is Hamiltonian, but it's not hard to check if it's Eulerian. It's pretty easy to check if it's Eulerian. Are there any questions about this? So since it's hard to check if a graph is Hamiltonian, you shouldn't expect for me to give you a nice theorem like we had last time, like Euler's theorem, where you basically can just say, oh, if the degrees are whatever, then the graph is Hamiltonian, right? So there's not going to be a nice theorem like that, which kind of characterizes everything. Instead of giving you a kind of perfect characterization, though, what I can do is give you a sufficient condition. So I can say, so I'm going to give you now a proof of a theorem called Dirac's theorem, which says that if a graph has a certain property, then it's Hamiltonian. So before that, I need a definition. So let delta of G, so little delta of G, be the minimum degree in the graph. So remember the degree of a vertex, right? If I've got a vertex V, the degree of V in G is the number of edges coming out of V, which in this case is 6, right? And the minimum degree is so delta of G, little delta of G, is defined to be the minimum degree of over all the vertices of G. And maybe, even though we're not going to use this terminology or this notation yet, I may as well just, for completeness, give you another definition. So capital delta of G is the maximum degree. So max of the degree in G of V, where it ranges over all vertices of G. So this is, this is like these are Greek letters, right? This is like lowercase delta, and this is uppercase delta. It looks like a triangle. So Dirac's theorem says that if G is a graph with, let's say, n vertices, where n is at least 3, and if the minimum degree in G is at least n over 2, then G has a Hamiltonian cycle. So here what we're giving, so this is a sufficient condition, right? This says, if I look at just these special graphs which have this special property that they have minimum degree at least n over 2, all of those graphs have Hamiltonian cycles. Okay, it doesn't really say anything about other graphs though. So it doesn't say like, it doesn't tell us exactly when you have Hamiltonian cycles or not, but it's just a sufficient condition. Any questions about any of these definitions or the statement of the theorem? If not, then let's get into the proof. Also, maybe I should just kind of highlight one thing. Remember in Euler's theorem, and when we were dealing with Eulerian graphs, actually we were dealing with actually a more general situation. So it was actually, instead of Eulerian graphs, we were actually looking at Eulerian multigraphs, right? Where you could have, between two vertices, you could have many edges. So here we're not dealing with multigraphs. So G is just a graph. That's something to keep in mind. And it's going to be important that G is a graph, not a multigraph. So that's one difference between these two concepts. You could also talk about a Hamiltonian multigraph, but there's not really any point because, even if there's two different, suppose there's like 5 edges between a certain pair of vertices, you only need to use one of them because the second one's not going to help. Okay, so this is just a statement of the theorem again at the top. And so let's get into the proof. So this is a very kind of a kind of standard approach in a lot of different graph theory problems, which is to consider a kind of maximal structure in the graph. So the structure we're going to look at is the longest path. Okay, so G is a graph. We don't know anything about it, but we can take the longest path in that graph, right? Every graph, every graph will have a longest path. Maybe that path is only one vertex, right? But anyway, there is a longest path. So just take any path which is of maximum length. So it's x1 up to xt. Now let's make an observation. So let's look at the endpoints of the path, right? So this is the longest path. Let's suppose I look at xt and I ask, where are the neighbors of xt? And if you think about it, like if xt has a neighbor that's like somewhere over here, not on the path, well, that would be a contradiction already, right? Because if I just take the path where I go from x1 to xt, and then I follow this edge to here, then that would be a longer path. Okay, so that's just what's written here. Every neighbor of, xt is on the path, or else we could make it longer. And by symmetry, the same thing works for x1, right? If it had a neighbor over here, we could make the path longer. So this doesn't happen. So therefore, the picture really looks like this. If I look at x1, all of its neighbors are somewhere on this path. Is that clear? Okay, so here is the next step. So what we've learned so far is that all of the neighbors of x1 or xt are on the path, right? On this longest path, x1 up to xt. So here's what I claim. There exists some number I between 1 and t minus 1 such that xi is adjacent to xt and xi plus 1 is adjacent to x1. Maybe I'll draw a picture to make it clear what I'm talking about. So this is our path. Let's say I've got xi and xi plus 1. And what I'm saying is that there exists some choice of I such that the picture looks like this. So I've got this. Xi is adjacent to xt, okay, and x1 is adjacent to xi plus 1, like this. So this is my claim. So how we prove this? I mean, at this point, we haven't used anything about the graph, right? At some point, we're going to have to use this minimum degree condition, but we haven't done it yet. So here's where it's going to come in. So let I, capital I, be the set of all I, little I, between 1 and t minus 1, such that xi is adjacent to xt, right? Which is like this is the property that we want, right? That's the same as this. So of course we are interested in these values of I. And we're also interested in some other values of I. So the values of I where xi plus 1 and x1 are adjacent. Now, I claim that the size of capital I is at least n over 2. So this is what I want to justify right now. Can anyone tell me why the size of I is at least n over 2? So what do we have to work with here, right? Our assumption is that the degrees in the graph are at least n over 2. That's one thing. And what we've already proven is that all the neighbors of xt and all the neighbors of x1 are on the path. So those are two things we've proven. So y is the size of I at least n over 2. Yep. So there's an answer in the chat, which is exactly right. So, right, because this, the number of neighbors of xt, so this set I, this contains all neighbors of xt, every single one of them, because we already proved that all the neighbors of xt are on the path. And this is literally, this set I is like all the indices little I such that xt and xi are a neighbor. And it's okay that we stopped here at t minus 1, right? Because xt is not a neighbor of itself. So that's not an issue, okay? So yeah, so this is exactly because, so this set I contains all the neighbors of x, and by assumption, there's at least n over 2 neighbors. So the size of I is at least n over 2, which is, of course, so the length of the path is t. So if the size of I is n over 2, then n over 2 is at least t over 2, because, of course, n is at least t. And the exact same argument tells us that the size of j is at least n over 2, which is at least t over 2, because j contains... so what defines a neighbor? So this is, something that I guess I defined way back before the break, so I can understand why people are forgetting it. But if u and v are neighbors, it just means that there's an edge between them. So these are neighbors. So it's the same thing as saying that they're adjacent or that uv is an edge. So for any vertex, like, the number of neighbors is equal to the degree of the vertex. Yeah. I think I introduced that terminology, but I understand I introduced a lot of terminology, so I can see how some of it maybe isn't sticking. Okay, thanks for the question. Any other questions right now? So I haven't finished this proof, but okay. The size of I is at least n over 2. The size of j is at least n over 2, which is at least t over 2. Now, I want to say that this implies that the size of I, the intersection of I and j is not empty. So intersection I of j is not equal to the empty set. And the reason is because if you look at it, I and j are contained in the numbers 1 up to t minus 1. So by the pigeonhole principle, which we learned about way back near the beginning of the course, so think of the elements of I and j as pigeons, and I've got t minus 1 holes. So for I, I've got t over 2 pigeons, at least t over 2 pigeons that go in those t minus 1 holes. And from j, there's t over 2 pigeons that go in those t minus 1 holes. So in total, there's t pigeons and t minus 1 holes. So the pigeons are the elements of j or I. So there must be some hole that has 2 pigeons in it. Okay, but that would be, what that means is that there's an element of 1 up to t minus 1, which is included in both of I and j. Okay, so therefore I and j have non-empty intersection. But if I just take some element little I, which is in the intersection, then it has the property that I wanted in the claim, right? So to kind of finish this off, take I in the intersection, and then it'll satisfy these two properties by definition. This slide is very messy, but is it clear? It's just a pigeonhole argument. Okay, so I claim that we're actually, so having this, this picture actually means that we're done. So why are we done? Okay, it does take a little bit of thinking. So now I found this I where xt is adjacent to xi and x1 is adjacent to xi plus 1. That's what we found. So this comes from the claim. So if I follow this along, like if I look at this green thing, right? If I follow x1 up to xi and then I jump over to xt, I go backwards to xi plus 1 and I jump over to x1. That's a cycle, okay? And it's a cycle of length t, and the length of that cycle has to be at least n over 2 and at most n, okay? Because, it's at most n because there's only n vertices. Of course, if it had length n, we'd be happy because it'd be a Hamiltonian cycle. And its size the length is at least n over 2 because all of the neighbors of x1 appear on this cycle. In fact, I could even say it's n over 2 plus 1 because it has x1. Okay. Now, here's the thing. This cycle has length at least n over 2, right? So I've got I'm now kind of redrawing this cycle here, but it has size at least n over 2. Suppose I've got a vertex y that's not on the cycle. Well, how many neighbors does y have? Or how many, what is the degree of y? Well, it's at least n over 2. But if I look at all the vertices that are not on the cycle, there's at most n over 2 vertices here. So this is the vertices not on the cycle. So where are y's neighbors? Like he can, y can have some neighbors over here, but it has at least n over 2 neighbors, and it's not adjacent to itself. So at least one of its neighbors must be over here, just because over here there's just, in the set of vertices that are not on the cycle, there's not enough room for all of y's neighbors, right? So here we're again using the fact that the minimum degree is at least n over 2. So y has a neighbor on the cycle, but that's a contradiction because it allows us to make a longer path, okay? Remember, x1 up to xt was the longest path in the whole graph. But now if I start at y, I go over to the cycle, and then I walk around all the way to the, the last vertex. That's a path of length, or path with t plus 1 vertices. But that's a contradiction because there isn't any path with t plus 1 vertices. Like we said, x1 up to xt was the longest path. Okay, are there any questions about this? So that's actually the end of Dirac's, the proof of Derox theorem. So similar to the proof of Euler's theorem, what's really important here isn't so much about knowing how to do this proof, although I think this proof wasn't that hard. I think, you could learn how to do this proof and it would possibly be helpful for you. The more important thing is that you understand the theorem, you understand the statement of the theorem, all the definitions involved, and that you could apply the theorem to a specific graph or to a kind of theoretical question where you're asked to prove that a graph has a Hamiltonian cycle or not, or something like that. So the more important thing is applying the theorem, but here's a proof in case you're interested. Right, and just to kind of, connect back to what we were saying before. So with Euler's theorem, it gave an exact characterization of Eulerian graphs. A graph is Eulerian if and only if, so it has an Eulerian circuit if and only if it's connected and all the degrees are even. Dirac's theorem is not like that, right? So Dirac's theorem says that if your minimum degree is at least n over 2, then you're Hamiltonian, but it's not, an if and only if. So of course there are Hamiltonian graphs which don't have degree n over 2, and the simplest one is just to take a cycle, right? If I just take, let's say, a cycle of length 6, this is obviously Hamiltonian because, it's clear how to find the path of the cycle, right? A Hamiltonian cycle is just this one. But here, n over 2 is 3, but the minimum degree is 2, right? So this is not a characterization. So there's no way to check if a graph is Hamiltonian by just looking at the degrees necessarily in general. Any questions about that? And so unless the degrees are large, right? If the degrees are this big, then you're happy. Otherwise, you're kind of stuck. So just a sort of side note. So some people may have heard of this, some people may not have. But so there's an interesting problem that's related to the Hamiltonian cycle problem. And that's something called typically it's called the traveling salesman problem. Although, the name of this problem goes back a long way. Obviously, traveling salesperson problem would probably be more appropriate. But it's usually known for historical reasons as the traveling salesman problem. So here's the problem. So G is a graph, and you think of each vertex as being a city, okay? And each edge is a road that connects two cities, right? And different roads might have different lengths, so you could label each road with a number, which is let's say the number of kilometers it takes to go from that vertex to that vertex along that road. And what the traveling sales person would like to do is to visit all the cities at least once. So what I mean is, at least once, And then at the end of the day, they want to return home while minimizing the distance traveled, right? And this is kind of similar to a Hamiltonian cycle, right? So in a Hamiltonian cycle, you took a graph, you wanted to visit every vertex just once and arrive back where you started. So in the traveling salesman problem, so it's a kind of optimization problem where you want to visit everything at least once and you want to minimize the cost of that trip. But of course, like, this is related because, if we had every edge having weight or length 1, right? So if the distance between any two cities is 1 kilometer and we wanted to say, is the answer equal to n? Like, is the minimum distance n? Well, the minimum distance is n if and only if, where n is the number of vertices, if and only if there's a Hamiltonian cycle. So there is some kind of connection between these two problems. So I just wanted to mention this for your mathematical education because it's a very important problem in optimization, and it's connected to Hamiltonian cycles. Is there any questions about this? Is the setup clear here? So you don't yeah. So in particular, because like I said, it's hard to find Hamiltonian cycles, right? So in particular, it's hard to solve the traveling salesman problem.